Hey everyone, before I start the conversation about implicit differentiation, which is the next lesson, I want to go ahead and review and recap everything we've learned about derivatives. First and foremost, we learned that the derivative is the slope of the tangent line and also the instantaneous rate of change, so I'll just call that IRC, instantaneous rate of change. And then we learned how to take the derivative using different derivative techniques. Before we did that, we talked about the definition of the derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all over h, or the limit as x approaches c of f of x, minus f of c all over x minus c. Okay. Then we learned how to take derivatives using different rules. The first rule we hit was the power rule, where the derivative of x to the n power is equal to n x to the n minus 1, really times dx, but dx is always 1. So after that, let's go ahead and go into the chain rule, which is basically, it is the power rule, but we go ahead and show it using composition of functions, so f of g of x. And the derivative of f of g of x is equal to f prime g of x times g prime of x, d outer, d stuff. So f prime of g of x times g prime of x. We did our product rule. We did 1d2 plus 2d1. We did our quotient rule. I'm just going to shorthand here, low d high minus high d low over low squared. And lastly, we talked about our trig. And when we have basically just sine of an angle, cosine of an angle, just a basic trig expression, it's d trig d angle. And we saw many problems where these rules all overlapped with each other. Okay? And the most important thing is that when we did these problems, when we were deriving, when we were taking the derivative of these functions, all of these functions were, for example, like y equals x to the third plus 2x minus 5, or f of x equals sine of x squared. And we would take the derivative, and I was forcing you to be very particular about your notation for a reason, because really the derivative of y is y prime, and y prime is equal to 3x squared plus 2. The derivative of f is f prime, and that is cosine of x squared times 2x. And then another way we can say y prime is dy dx. So the derivative of y is dy dx. But there are many times where the equation is not necessarily already solved for y. So notice how this is y equals da 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 da, f of x equals da 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 da. What if the equation is not solved for y? Well, in these problems, in these functions, because the equation was solved for y, we were doing something called explicit differentiation. Explicit means that the function is already a y equals. So when we derived, it was just y prime equals, or dy dx equals. When the function is not explicit, when we have not solved for y, some of you may say, well, why don't we just solve for y and derive? Sure, but what if we can't? What if it's too complicated? Let me show you a few examples. So here's an example of an equation that is not solved for y. So it is not explicitly stated that it is a y equals equation. It's not terribly difficult to solve for y and then derive to find dy dx, to find the derivative. It's not terribly difficult to isolate y and derive, but it really is a waste of time. So today we're going to talk about implicit differentiation. So implicit differentiation. And what implicit differentiation means is we're still taking the derivative, we're still using all the rules that I just reviewed with you, but our equation is not isolated for y. Okay? So here's how you do implicit differentiation. We're going to take the derivative, just like we did before, of every single piece. Just like we did explicitly. Let's say explicitly, again, you've got y is equal to x squared minus 5x. We took the derivative of every piece. We said dy dx, or y prime, is equal to 2x minus 5. Okay? We took the derivative of every piece to create the equation for the slope of the tangent line. So we're going to do that. We're going to do 2x plus 2y dy dx is equal to 0. When we take the derivative of x, we are taking the derivative of x with respect to x. So this is kind of an unnecessary statement because that simply means a value of 1. But this is a very necessary statement because we're taking now the derivative of y squared, where before we were simply just saying, okay, the derivative of y is y prime. Well, now it's the derivative of y squared. The derivative of y squared is 2y dy dx, d stuff. Where here we were doing dx dx, or d stuff, quote unquote, was 1. Here it's 2y dy dx is equal to the derivative of 25, which is 0. Once you derive each piece, so once you derive each piece and you don't forget your dy dx's on your y's, your next job is to isolate dy dx. So let me go ahead and move him because this is just 1. So let me rewrite that. We have 2x plus 2y dy dx is equal to 0. Now we have to isolate dy dx, so let's subtract 2x to both sides and divide by 2y. So the derivative of y with respect to x is equal to negative x over y. That is the equation for the slope of the tangent line for this circle. That's a circle. X squared plus y squared equals 25. That's a circle with a radius of 5. Okay? And every tangent line on that circle will have this formula for the slope of the tangent line. So let's say we want to find, let's not move that. Let's say we want to find the slope of the tangent line at the point, I don't know, 1, 3. So find the slope of the tangent line of this circle at the point 1, 3. Well, we would find the derivative implicitly, because this equation is not solved for y. Find the derivative implicitly, and then dy dx at 1, 3 is equal to negative 1 over 3. I plugged in 1 for x, 3 for y. So now let's do some from the manual.